We're all familiar with waves, especially water waves. But sound and light are just as wavy, and they're even more common. Luckily, we can learn a lot about sound and light waves by looking at water waves. Here are some continuous circular waves being made by a point source, as shown from above, so that we can see their crests moving outwards. We can also show the waves side on, where it's easier to see what's making them. For example, here a rod is being dipped in and out of the water. How would you describe a wave to a friend? We can describe the waves using their wavelength, which is the distance between their crests. It's also the distance between their troughs, because this is the same distance. We'll call the wavelength lambda, which is a letter that stands for L in the Greek alphabet. Now we'll fade out the overhead view and just look at the side view to make the waves look simpler. And here's a boat to show some of the strange properties of waves. How is the boat moving differently to the wave? Notice how the wave is moving left to right, but the boat only moves up and down. You can check this out next time you're in a boat. The speed of a wave is how fast it's travelling from left to right here, and is usually given the symbol v, which stands for velocity. Velocity is another word for speed. Notice how the speed of the wave is constant, and each crest moves at the same speed as the others. But the boat's up and down speed changes, and you can see that it's moving fastest in the middle of its cycle. This cyclic type of movement is called simple harmonic motion, and we'll cover that later. A pendulum is another example of simple harmonic motion, although it moves horizontally instead of vertically. The amplitude of a wave, with symbol A, is how high it moves up and down compared to a flat, calm surface. Higher amplitudes are caused by the source having more energy and dipping further into and out of the water. The guy on the boat would notice that he would rise and fall more, so he'd get a more energetic ride. The wave's frequency, given the symbol F, is the number of waves being made each second. The frequency is also the number of waves passing by the guy in the boat each second. Here, only one wave is passing per second, so scientists say that its frequency is 1 Hertz. Hertz is the unit of frequency, and it just means waves per second. It's usually shortened to Hz. This unit was named after the famous German scientist Heinrich Hertz, who proved the existence of electromagnetic waves, which we'll explain in another video. Interestingly, Hertz was not only a clever scientist, he could also speak Arabic and Sanskrit. Both of these languages are steeped in scientific and mathematical history. Does anything happen if we increase the frequency by dipping the source in and out more often? Let's double it, from 1 to 2 Hertz. Looking at the wavelength, we can see that it gets shorter. We doubled the frequency, and the wavelength looks about half what it was before. This means that when frequency increases, wavelength decreases, and vice versa. So we can say that frequency and wavelength are inversely related. That makes sense. When we increase the frequency, more waves are squeezed in, reducing the distance between them. We've looked at wavelength, frequency, amplitude, and speed. In the next video, we'll show how these can be mathematically connected to each other with the wave equation.